This is a demonstration of proof by induction. We seek to prove the theorem that n squared is less than or equal to 2 to the n for integer values of n greater than or equal to 4. When we begin the inductive proof, we want to be very clear about our predicate. In this case, our predicate p of n is n squared is less than or equal to 2 to the n. Now, we must begin by proving the base case. We see that this is to be true for integer values of n greater than or equal to 4. Our base case then is n equal to 4. Now this may seem unusual. Often base cases are either n equal to 0 or n equal to 1, but in this case our base case is going to be n equal to 4 because this result, that is n squared less than or equal to 2 to the n, is in fact false for n equal to 3. It is true for n equal to 0, 1, and 2, but it is false for n equal to 3. It is true for n equal to 4, and we will begin our base case with n equal to 4. So, why does the base case hold? Well, that's easy to see. It's because 4 squared is equal to 16, which of course is the same as 2 to the 4th. So the base case, p of 4, holds. Now we want to do the inductive step of the proof, so we will assume that p of n holds, and we want to prove that p of n plus 1 follows. P of n holding says, of course, that n squared is less than or equal to 2 to the n. What we want to show from that is p of n plus 1 follows, that is, n plus 1 squared is less than or equal to 2 to the n plus 1. To do this, we're going to go through a chain of inequalities. So we will begin right here with n plus 1 squared and expand that to n squared plus 2n plus 1. Now we're going to replace the 1 in the previous inequality by n, and we are allowed to do that because our assumption is that n is greater or equal to 4, and therefore, of course, it is greater or equal to 1. So we replace the n by a 1. That's nice because it'll give us a total of 3n right here. Now, we replace the 3 in the 3n by an n, and we're allowed to do that because, once again, n is greater than or equal to 4, therefore n is greater than or equal to 3 as well. So we replace this 3 by this n right here. Now we can combine these two terms right here and recognize that that's simply n squared plus n squared, or 2n squared. Now that's still not quite what we want up here, but we're almost there. In fact, we haven't used the inductive assumption yet, but we will now, because we will replace the n squared right here by 2 to the n using the inductive assumption. So we have 2 times 2 to the n, which is of course 2n plus 1, and to get that we use the inductive assumption. So we have shown that if p of n holds, that n squared is less than or equal to 2 to the n, then p of n plus 1 follows, and that is that n plus 1 squared is less than or equal to 2 to the n plus 1.